Okay, so during today's webinar, we'll talk first about Matteo Vettori will make an introduction about composite material and their theory. Then I will show you some example of composite material in midas NFX. Then we'll go back and show you some project applications of composite materials. Okay, Matteo, are you ready?
Thank you, Cyprian, for the introduction. I will start with the definition of a composite material. I haven't been able to find out a better definition than those on Wikipedia, and so I give it to you. What is it, a composite material? A composite material is a new material made from two or more constituent materials that are significantly different one from the other, maybe for different physical properties or chemical or also mechanical properties. When combined together, the two or more constituent materials gives out a better material with better characteristics, different from those from the individual components. One particularity of the composite materials is that the individual components remains separate and distinct within the finished structure. This means that all the constituents can be defined and identified into the composite architecture. The new material may be preferable from the single constituents because it gives better mechanical properties or better weight and so on. A typical example is the use of composite fibers. If we think of using the fiber itself, it will be impossible to have a stable manufact, but used as a composite, we have quite the same properties of the fibers, but they can be used and they can be shaped into the manufact itself. We can have four different families of composite materials. We start with particle composite. The concrete is an example. The reinforcement material is dispersed into the matrix materials and it has the shape of particles. Then we have a short fiber composite. In this case, we have a composite made of fibers, the reinforcement made of fibers, and these fibers are of a short length and they are dispersed into the matrix. Moreover, we can have aligned fiber or randomly disposed fiber. In the first case, we will have directional properties of the final material, and in the second case, we will have quite homogeneous properties of the material. When then we talk about long continuous fibers, we mean the use of long fibers that are bundled together with a matrix made from a resin, an epoxy resin or phenolic resin, for example. In this case, the example is those of laminate materials in which long fibers are disposed to form the lamina, and the single fibers are bundled together thanks to the resin. Then we have the laminated composite. Laminated composite that can be made of single laminas of long fiber composites or also of laminas of homogeneous materials. When we consider a composite manufact, we see the outside of the material, but if we can cut the manufact, we can see that the material is made of a laminate composite mainly. In this case, we will see the stacking sequence, maybe the stratification of the material on the manufact, and if we can go in deep with the magnification of our investigation, we can see that maybe the single laminas are made of different kind of materials. If we consider the laminas, we can have different kind of laminate materials. For example, we have unidirectional materials that are made of fibers all aligned together along a principal direction, and also we can have textiles or woven materials that are made of fibers of taus of fibers that are weaved together with different architecture. With the terms architecture, we means the way the single taus of the material are weaved together, forming the final lamina of the material. We can use homogeneous fibers, also we can use heterogeneous fibers, as those in the last picture. We can see Kevlar fibers, the yellow one, that are weaved with the carbon fibers. This gives better performance, for example, in terms of flexibility and in terms of surface resistance. Then we have another form of composite material, that is the 3D textiles. In this case, we have no simple laminate material, lamina material, but we have a 3D material that is preformed in a final shape, for example, those of a beam or something like that. If we go in deeper again and we consider the single tau of the material, we can see the fibers that are nested together into the microstructure of the tau itself, and we see that these fibers are all around coupled with the matrix material. In this case, we have matrix that is filling the void between the fibers. If we go moreover in deep, we can see that we have the fiber, and this length of investigation is useful to define maybe the mechanism of damage of the fiber itself. And but at this magnification, we can see that the fiber appears to be homogeneous. But if we go in deeper, we see that the chemical structure of the fiber is made of plies, or better sheets of carbon molecules that are then wrapped together into the fiber itself. When we talk then about finite element simulation of a composite manufact, we have to consider different scales again. When we talk about manufacts and structures, we are at the component scale of the material, that is the macro scale of the material, and in this scale of investigation we consider the big structure and the components made by composite materials. We use this scale to design the final manufact. When we want to design the material itself, or better, when we want to design the architecture of the material, we have to refer to the mesoscale. So with finite element analysis, we can design the shape of the architecture of the material to, for example, have specific properties along maybe some load directions and so on. At wider magnification, we reach the micro scale of the material, and we can consider, for example, the nesting of fiber or the fiber fracture mechanism in terms of simulation. Which are the pros and cons of composite materials? We know all that composite materials are lightweight, they give high stiffness and high resistance, but they are not cheap, they are expensive material. And another fact is the complexity of designing with composite material. I mean, we cannot use the simple formulas of the machine design theory, but we need to use specific formulas for designing with composites. If we look at the Ashby map I just copied here, it is the map that plots Young modulus versus density, and we can see that composite materials are really close to aluminum alloys. This is the reason because composites are also called as black aluminiums. We have very close properties. So why is preferable to use composites for lightweight and for really high-end applications? The answer is the tailorability of the material. We can design the material into the manufact in order to have the desired properties of the material in a specific point of the manufacture. This is the main advantage, and so we have infinite possibility of optimization and customization of the material into the manufacture. How to do that? We need to know some theory, and we need to have some background about classical lamination theory, so the formulas that are used to design with composite materials. We need to start from the concept that isotropic material have two constants for knowing the behavior of the material. So we need Young modulus and Poisson ratio to know how the material behave when we apply a stress. So we can correlate with these two constants the stress and strain field of the material. When we have to work with an anisotropic material, we need to use 21 constants to define the elastic properties of the material. So these 21 constants are needed to define the compliance matrix or the stiffness matrix of the material. What about when we consider the single lamina? The single lamina is classified as an orthotropic material, so we have directional properties that are orthogonal between each other. So we just need 9 constants. This number comes out from the fact that also the compliance matrix is symmetrical, so we need only these 3 by 3 by 3 9 constants of the compliance matrix. So we need these 9 constants to build up the compliance matrix that correlate the stress field to the strain field. If we look at the generic expression of the matrix, this is the form we have, and thanks to the symmetry we can define this relation that links together the stiffness properties, so the Young modulus of the materials along each direction, with the Poisson ratios. If we just assume that we can simplify the material as the behavior of the material as a plane stress behavior, and this is not a so big assumption if we consider that the single laminas are commonly very thin laminas, so we can use this through the thickness simplification. We just can simplify also again the matrices, and we arrive to a 3 by 3 matrix that describes the stiffness matrix of the material. Inverting, we can have the compliance matrix. So we have defined the complete stress-strain field and relation of the lamina, of the single lamina. This is made for a reference system that is aligned to the material properties. So if we use the material reference system, that is those which has principal axis aligned to the material direction, we can use the previous matrix. But if we need to define the elastic properties and the behavior of the material along a different reference system, a Cartesian reference system that is not aligned to the material, we need to define the angle of misalignment between the two reference systems, and we need to define a new matrix of compliance or a new stiffness matrix. In this case, we can link the two matrices, those in the material reference system and those in the generic reference systems, only with simple trigonometric transformations. So we can calculate the generic matrix starting from the simple matrix in the material reference system. If we look at the term of the generic matrix, we see that we have new terms that are non-zero. These terms are called the coupling terms, and those are responsible of a twisting of the lamina if we apply a longitudinal load. So for a composite material that is loaded along a principal direction onto an off-axis reference system, so a generic reference system, we will see that not only direct stresses are generated, but we will have also deformation along not deformation, but we will have twist along the both x and y direction. In this way, this kind of twisting is defined by the coupling terms. If we plot the material, the stiffness matrix of the material, we can see that we have a particular behavior of each term. If we see, we plot these terms in terms of the orientation angle of the material onto the generic reference system, and we see that the Q11 and Q22 term are maximum and minimum at 0 and 90 degrees. That is what we can imagine. If we plot then the terms Q12 and Q33, we will see that we will have a maximum at 45 degrees of orientation. This means that the lamina results in a maximum shear stiffness when fibers are oriented at 45 degrees, and it results also in a maximum transversal deformation if we apply a longitudinal, so a direct stress along the x or y direction. Moreover, if we consider the Q13 and Q23 terms, so the coupling terms, we will see that this maximum distortion, so the maximum of these coupling terms, are reached at 30 and 60 degrees. So at that angles we will have the maximum distortion of the lamina. How to consider then a laminate? We need to use the classical lamination theory, that is also called the CLT. Hypotheses at the background of the classical lamination theory are the following two hypotheses. Laminas are perfectly bonded together, so shear stresses are rigidly transferred between laminas, and the fact that a generical through the thickness section of the laminate deforms remaining perpendicular to the laminate midplane. This is also known as the Kirchhoff law of assumption or behavior. If these two hypotheses are real, so we can say that displacement and deformation are continuous through the interlaminar interface, and shear and deformability is, and the fact that the shear deformability is negligible for the laminate. So we can use the theory of shells. Then we consider the unit cell of the laminate, so the single unitary element, and we can define these loads per unit of length that are acting through the thickness of the laminate. The normal and transversal shear loads, and the moments that are flexural and twisting and torsional moments acting on the plane. If we assume that if we consider that these loads are generated by the stress through the thickness, we can integrate through the thickness of the lamina the stresses, and we can define the single load components as the integration through the thickness of the lamina of the stresses that are applied on each lamina of the laminate. Moreover, we can define the generical deformation of a point through the thickness as the combination of the deformation of the point onto the mid-plane of the laminate and the rotation, the rigid body rotation of the Z point with the terms kx, ky, and kxy. If this expression can be simplified in this way. If we then explode the term that gives the N and the M load components, we can integrate partially onto each lamina what happened to the complete thickness of the laminate. So we can divide the integration through the entire thickness of the laminate as the summation, as the sum of the single integration onto each lamina thickness. Just substituting the formulas, the matricial form for the single laminas that links stress to strains, we just arrive to these final terms where the N and M components are expressed in terms of what happens in terms of deformation onto the single laminas. We can then describe the previous formula in this matricial way, in which we have the load and the displacement and the deformation of the laminate, and we have this matrix that is called the ABD matrix, that is at the basic of the classical lamination theory. The terms A in the ABD matrix, it is related to direct stresses, and this is given by this, each term is given by this definition, and it is a composition of the single terms of the Q matrices of the single laminas that build up the laminates. So, from the stiffness matrix of the single lamina, according to the stacking sequence and according to the thickness of the single lamina, according to the stacking sequence of the laminate, we can build up each terms of the A matrix of the ABD. The same for the B matrix, that is the matrix of the coupling terms, and again the same for the D matrix, that is the matrix of flexural stresses. So matrix A is related to NX, NY and NXY stresses. The B term is the coupling term, and the D terms are related to the flexural DM terms of the matrix. In this image, we just define that when the single terms of the laminate are mainly populated, we have to say that when we have a non-symmetrical layup, we will have B terms non-zero in the stiffness matrix, and also when we will have orthotropic material, we will have A and D terms that will be I terms, so non-zero terms. We can define some particular layup in terms of what gives out in this ABD matrix. We define a symmetrical layup that is made of homogeneous and orthotropic material that are stacked symmetrically with respect to the center line, so the mid-plane of the laminate. We will have the same angles from the both sides of the center line. When we have same angles but negated, we talk about an antisymmetrical layup, so we have the same angles but negated. And at the end, we talk about a balanced non-symmetrical layup when we have each angle of the laminate that is present in plus and in minus terms, but these angles are not disposed symmetrically. So angles, the behavior, the final behavior of the material is a non-symmetrical behavior. Moreover, if we consider some particular angles, we can define a cross-ply laminate that is made of 0,90 plies, and we can have the angle ply laminate when we have single angle that is repeated plus minus through the thickness. We talk about a quasi-isotropic laminate when we have this specific static sequence which gives out somehow of homogeneous properties in the plane of the laminate. So we talk about isotropic laminate because the property on the plane of the laminate are quasi-isotropic. How all this theory is used in the finite element. Finite element approach requires specific element formulation for composite material. In general, we have two widely used type of elements for composite analysis. We have plane element and the solid element. The laminate shell elements are the plane element and they are the widely used element. The solid elements are typical of high-end simulation software. Which are the characteristics of both these elements? Laminate shells are 2D elements. They have the characteristic of define the thickness of the laminate in one element only. So we have one element to the thickness of the laminate. But we can have 3 or more than 3 integration points to the thickness. Usually we use 3 integration points for each lamina. So we have a good description of the flexural behavior for each composite lamina. They use orthotropic material to define the property of the single lamina, and they need to be defined in terms of layup definition and in terms of ply thicknesses, because the thickness of the laminate is calculated from single ply thicknesses and from the layup definition. Laminate elements are commonly used for the generical analysis of a composite structure, and they are really good for plane stress problems. Then we have solid elements. In the case of solid elements, we can have more than one element through the thickness, and we can use them to describe better 3D geometries, or for example the drop of ply situation. In this case we can have a maximum, also we can describe one single lamina of the laminate with a single element to have a better description, or also more. They will use orthotropic material. The ply thickness is necessary to define the thickness, and the layup is necessary to define the layup. What is really important is that if we don't want to have distortion, we need to describe, to have the thickness of the solid element that is equal to the thickness of the layup that is represented by that solid element, and this is really important. With this, I have closed the theoretical background, and I give back the voice to Cyprian for the second part of the webinar.
Thank you very much, Matteo. Okay. I will change my screen so you can see. Okay. Thank you for this introduction to composite materials. Very interesting theory, and I saw also that you didn't steal your PhD degree. Okay, so I will go up with a tutorial on midas NFX to show everyone how to assign these composite materials, and I will use a simple model, which is the plate, so that you have here on the screen. So the model I have now is only geometry, so I will show you how to create the mesh, how to assign the material and everything from the beginning, so you see how you can create good mesh for composite analysis, because this is a critical issue. So the first thing is to create the material. So we do as usual, you add I will do like that, material. So you can add isotropic material. So as we do usual, you go in the library or you enter your own coefficients. And we can create also 2D orthotropic material or 3D orthotropic and enter the coefficient which are related to this type of material. So as Matteo presented, this is the kind of material we use frequently for composite analysis. So here I already have one 2D orthotropic material that I will use for this simulation. So it is an ACE P4 PKSI, and here you have all the coefficients that I entered. Now, to create the layup of the composite material, you have to go in the property window. As you create a plate property, you go in 2D. So in midas NFX, you have the possibility to use composite into 2D analysis, 3D model also. And you can use it in linear, nonlinear, and dynamic analysis as well. So in this window, you have to choose composite shell for 2D. So I can change the name to composite. And you have several options here. So the first thing is you can use or not the global ply ID. You have several failure theory which are provided to analyze your composite. So Hill, Hoffman, Tsai-Wu, maximum stress, maximum strain, or a NASA Lark criterion. All that can be defined. So now the main step is to create the stack sequence for the material. So I will create some layups. So the only thing to do is to add the material you want to use and add the adequate orientation angle, so 0 for the first one. Here you have to choose yes if you want to output the results. Now I will do a small layup of this material, so the second angle will be -45. The third one is 45, and the last one is 90 degrees. And you can use this overall laminate symmetry in order to make the two sides symmetric. So this is a quasi-isotropic laminate, as I learned it during Matteo's presentation. Okay, you can see the laminate preview here. So you have here it will be the layup with the different orientation angle and the thickness of the different layups. You can also click the button Show the Laminate Properties, and it will output the composite matrix with all the coefficients calculated. Now I'll click on OK. I will not define any failure criteria for this example. And I'm ready for the meshing of this model. So in order to use composite material, you should use either hexa mesh or penta mesh in 3D. So for 2D analysis, the best way to use composite is to create manually the mesh in order to be sure to have the perfect meshing. So I will use the generate mesh for 2D, and you have several tabs here. The one we use usually is the auto face or auto area. But in this case, in order to get the best meshing, I will use map area. So I just have to select the areas to use to enter the appropriate size, so 1 millimeter. Here I have the composite property that I just defined, and you can preview, so it will give something like that. Apply. Now for this second part, which is a bit more complex than this one to mesh, I will not use the automatic mapped boundary. I can show you what it will give if I do that using the preview. So you see it will give a mesh like that. So in this area the mesh will be bad. So in this case I will change to manual mapped boundary, and there's a trick. You have to select like that, the group 2, the main edge here, group 3, and for the group 4 you select these two edges. So if you do that, you see the mesh will be really good. And there's one thing you need to check, is if the merge node option is activated or not. So, because if it's not, the nodes will not be merged at the interface between the two plates. So I click on apply. And now, to mesh the other two parts, I will use again the automatic mesh boundary. So I will simply select the 4 edges here. The size will be 10 millimeter, so it will give something like that. And do the same for this side. Apply. And finally this side. Okay, so now I have 1/4 of my plate which is meshed. So what I have to do is to create the full model. So to do that I will simply use the mirror option to mirror the mesh. But before doing that I will merge these mesh sets together. So I select all the mesh sets, right click, merge. In order to create only one mesh set, it will be more easy to mirror it. In the mesh tab, you have all the options to work on the mesh, and here you have the transform mirror option, which will allow you to directly select a plane and to mirror the mesh. So don't forget to preview. You will know if you selected the right plane or not. Now, selecting this plane again. Okay, now I have my mesh sets. I will merge it together again. Okay, and now let's assign a boundary condition to this plate. So what I will do is I will simply fix one end. So click on constraints, select the nodes on this boundary and fix them. And on the other end I will apply a displacement here in X direction. So I will apply 1 millimeter. I will perform a linear static analysis, so be careful not to import a too large displacement. And now there's something that sometimes the people who don't know forget, is to check the material orientation. So you have, because it's important for the composite that all the elements material orientation are in the same direction. So in the small icons here you have show hide the material sources, so I will check that. And if you zoom on it, you see that the material orientation is not the same in all the mesh sets. So if you perform the analysis like that, you will get some strange results. So in order to change that, you have to go in the Mesh tab, Parameters, 2D, Parameters, and here select all the mesh. And you have Add Material Orientation. So here you see all, I will put all the elements in the X axis, so you can preview. Okay. And if I activate again, you see that now it's correctly set. So all the orientation of the material is in the same direction than the load. Okay, I activate that again. And I just have to create the analysis case. So I right click here and I create a linear static analysis case. And I solve it. Okay, now in 5 seconds NFX give me the results. So by default I have only one type of result, which is the total translation. I will add more results, so to do that you have to right click here and insert analysis results. So if you check, you have some results for all the plies of the composite material. You have also some results for the composite maximum, the minimum, the shell element forces, the reaction, the grid force. So what I will do is that I will add the 4 meter stress for the ply 1, and I will add also the 4 meter stress for the ply 2, and the 4 meter stress for the maximum. So I will only activate these 3 components for the moment. So you see it appears here on the left. I will hide the geometry because I don't need it. So I'll go in the geometry here, hide all, and show the mesh edge. Okay. So now if I checked here the shell maximum for meters, so it will give me the maximum of all the plies on my plate. And here the top one, for example, and the top 2, and you have some special tools to check composite results, which are in the composite here, through the thickness plot of ply results. So if you use this option, you can check some elements of the plate, and the stress between the plies will be shown in this window. So from the ply 1, 2, 3 until the ply 8. So of course you see it's symmetric because I made a symmetric laminate property. Here it's for the shell normal one, but you can check the form midas also. And you have some complementary tool to check the contour and the isoline for plots and composites. So in using this tool you can check the data of the contour of one composite. So here it's a maximum for this normal 1-1, and the isoline, which is corresponding to another criteria. So for example, you can check for the form midas isoline. So you can see the two on the same graph. Okay, so now it's all for this simple plate example. I have another example that I would like to show you, which is this one. It's an example of a nonlinear analysis, so I already defined everything. And it's only, I have 3 mesh sets. I'll show you the boundary conditions. So this plate is fixed like that around. I have a static displacement on these parts, and I have some contacts between the two. So between these two elements in blue, I have a simple welded contact, and between the other parts, the blue one here, the thin plate, and the big plate, I have a breaking weld contact. So this is a type of contact that midas procures, and which helps to see the breaking of the contact during the analysis. So you can use that with composite material as well. So in order to show you that, I've assigned 3D composite material to the plate, which is the thinner of this plate. So to assign 3D composite material, it's exactly the same than 2D. So you have the stacking sequence. So what I define is simply 2 alloy steel which are symmetric, 0 degree and 90 degree. And I will show you the results. So first of all, the displacement. So I will put first to real, so it gives me something like that. So this is nonlinear static analysis. So when I go through the steps, you see the form of the behavior is changing. It's difficult to see, so I will increase the scale and come back to the beginning. So you see from there, when the analysis continue, the contact is breaking with the plate, and finally I have something like that. So there's a space between the two, and this plate is made in composite material, so I can check the result for composite as well. And this is the fall midas stress for the ply one. So it gives you something like that. Of course, I increase a lot the deformation. It's quite small, actually. But it is to show you that the composite can as well be used into three-dimensional analysis, and you can use also this breaking weld analysis in order to analyze this kind of behavior. Okay, so it's over for my demonstration. I will give back the hand to Matteo, who will show you some project applications.
So here I am back. Sabrina, I would like to start my second presentation with this image, because your presentation and your example brings at my memory that we didn't talk too much about orientation. As I've said before, it is really important to define the orientation of the material into the lamination and into the stacking sequence, and also for the single lamina, because the stiffness properties are really different between within different angles of orientation. The same, it is really important to define the orientation of the material into the finite element model and into each finite element, because if we didn't specify this material orientation, the measure will generate randomly the material orientation, and in this way we could have some discontinuities, some sudden changes into the material orientation between one element and the adjacent elements. In this way we will have the sudden change in the orientation will generate a sudden change of the stiffness matrix of the element and the stiffness matrix of the lamination and of the laminate. So it will lead to wrong results, but also to sudden changes into the stress and strain field of the model. So my remarks is to pay attention and to remember always to define the material orientation into the finite element model in a proper way, in order to describe well how the material is applied and how the material is oriented locally. Then after this I will start telling you some success story we have had here at the University of Parma. The work that I will present is the final graduation project of a student of mine, Lorenzo Bergonzi, that just graduated a few days ago. His work is about the structural analysis of a Formula SAE car frame made of composite pipes. We need to say and to specify that each pipe has been linked to the other by the means of adhesive bonded joints. These joints have been idealized as shown in the picture, and the study will start from the generical study of the global model of the frame and will end with the evaluation of the bonded joint, of the worst bonded joint, by the means of a sub-model of the bonded joint itself. The work started from the CAD model of the frame, actually the work started from the wireframe of the car, so the axis of each beam element. This axis has been imported into midas NFX, and onto each axis has been defined the finite element model, applying the correct section for each beam. Then the model has been completed with other elements and other type of finite elements. So it is the global model is made of 1D, 2D, and 3D elements mixed together and linked together. Because the model is representing also the suspension triangles, it is really important to define the correct nodal releases in order to describe well the kinematic of the frame. Then the model has been completed with load and boundary conditions. The second model, as I told you, we have done a submodel of the bonded joint, an idealization of the joint. The model has been built manually, starting from a 2D mesh that has been revolved. The model is made of 3D elements, and a good attention has been paid to the mesh size and local refinement of mesh in order to have a good description of stresses. The bond, the glue has been discretized with 2 layers of 3D elements in order to have an accurate stress distribution, and contact, a bonded contact has been used to link the glue with the aluminium and both with the composite part of the joint. The composite has been represented with 2D shell element, laminate shell element, and the stacking sequence has been defined into the element definition. Then the shells has been glued to the adhesive element, taking into account also the gap that is produced by the fact that we use the mid-plane of the carbon pipe instead of using the full thickness of the pipe. We need to define a local coordinate system for the 3D element of the glue, because to be able to evaluate the correct stresses onto the glue. So when we talk about a bonded joint, the stresses that needs to be considered are the peeling stress and the shear stress that is shown in the picture here. This picture shows you some of the loading conditions that we apply to the model, and how we validate the model starting from the results of the global model. So we evaluate the displacement and the stiffness of the frame from the global model. Then we go through the investigation of the bonded joint. How we transfer the load, we define from the global model, we defined the most loaded joints, and we applied to the local model the loading conditions representative of this worst node. So we extrapolated from the global model the normal, the transversal, and the flexural and the torsional moments on the frame, and we applied this near the bonded joint, and we applied this action directly to the local model by the means of a rigid element spider, in order to be able to apply these loads to a single point or single This is an overview of the results. So we have been able to evaluate both what happens globally on the frame and what happens locally on the bonding joint. A second example I would like to show you is again a part of the project of Lorenzo Bergonzi, which has validated the software for composite analysis. Before to start his master thesis project, his work has been focused on the validation of the results of midas NFX when using the software for composite analysis. So we took an FEMS publication, that is written here, and we just reproduce the benchmark that are proposed, and we correlate our results, so the midas NFX results, with the results proposed onto the paper. Different kind of stacking sequence are proposed. Here I will show only some of these results, but the same correlation can be found for each kind of layup. In this case, we just correlate the ABD matrix terms from the classical lamination theory proposed by the book and the midas NFX results. And we can see that we have a really good correlation between the results, and this validates how midas NFX calculates the ABD matrix for a laminate layup. In the second example, we just compare how using a different stacking sequence, how the material or how the software calculate again the ABD matrix. So moreover, with a much more complex layup, we have again a good correlation of the terms of the ABD matrix. In this last example, we just go through the failure criteria evaluation. So midas NFX used different kind of failure criteria. We took in account Taiwu, Hill, and Hoffman because they were the failure criteria as proposed by the book, and again in each column is proposed the correlation between the theoretical results calculated by the book and midas NFX. And again, the software is quite able to evaluate the same results from the theory. Then this is another example of benchmark that Lorenzo Bergonzi has done, starting from a model of a full component. But Cyprian will talk about this, so I give back the microphone to Cyprian for the last part of the webinar. So thank you for the attention, and the microphone is for you, Cyprian. Stop.
Okay, so this is an example project application which has been provided by the University of Parma to Midas. So this is a composite boat analysis. So it has been studied using midas NFX. The boundary conditions that have been applied are the symmetry condition and the displacement TZ have been blocked at these two positions of the boat. So if I show you the model in midas NFX, it's here. So it's a semi-boat, let's say, and you can check as it is made fully with composite material. I will show you the ply components. So there's 1D material, and also these are all the composite material which have been used. So I will show you only one. So this is the stacking sequence that have been used for this composite. And if I see the laminate preview, it gives something like that. And laminate properties, okay. And you can use also the tool I've shown through the thickness plot in order to see the results of the ply by ply. So for 4 midas stress, for example. So you can check several positions of the boat to see the difference between the ply on this window. And if you don't have Midas NFX now, you can still request the 30-day trial on midasnfx.com. So you just go on midasnfx.com and request the trial, and we will send you this trial. So it is a full trial including all the capabilities of the software. So about Composite is included as well. Nonlinear, you can even use nonlinear dynamic or CFD analysis. Thank you very much for joining this webinar. And right now we'll have a short question session. So if you have some questions about all what we talked about during this webinar, please just write them in the chat section, and we will answer them here right now. So I've only 2 questions. One is if we can use customized failure criteria in Midas NFX. We don't support yet this capability, but we already have quite a range of failure criteria, and it is more than sufficient for the most of the users who use composite materials. Another user is asking about the anisotropy. Yes, as I told during the webinar, we can use 2D anisotropic material 3D also, and assign them to use for the composite materials. Okay, well, if you don't have more questions, thank you very much for joining, and I hope you will join our next webinar on the 6th of August. We are waiting for you. Thank you very much, and have a nice day.